Hello and welcome to Team 7's presentation for Senior Design at Clemson University for the fall semester of 2022. My name is Nick Sanborn and I will be introducing our project, objectives, motivation, and problem definition. Our objective for this semester was to develop a docking station for the Vauxhall M500 drone from Model AI. The docking station should be fully autonomous and include battery charging and network control. The budget for this project was $500, excluding the cost of the drone. Our project was, in part, motivated by the growing autonomous drone industry. We also recognized the potential for growth in the drone security market, where drones or other unmanned aerial systems can be deployed to investigate alarms or monitor areas in large industrial or commercial buildings. These drones require a docking station to charge and reset while not in use. This existing market for autonomous drone docking stations is currently small and units are very expensive, with most models costing thousands. This is why we were motivated to design a low-cost solution with the potential to deploy at a large scale to provide an alternative to the current options. When considering what features were necessary for the docking station, we determined that a battery charging circuit, protective housing, communication between the drone and station, and autonomous landing were all required. Our design requirements and solutions for each of these necessary features will be discussed in further detail in the following slides. The demonstration of each subsystem will also be given. Now I'll pass it off to Dakota, who will cover the hardware design.
Hi, I'm Dakota Tatro, and today I'm going to go over the hardware requirements, the hardware design, and the hardware implementation. As you can see here, the design requirements for the build required a system within 40 by 40 by 24 inches. This needed to be an enclosure that weighed less than 50 pounds to be easy for transportation and installation. The charging circuit required a 12-volt output to adequately charge the battery with the BMS, or battery management system. The charging circuit needed to provide enough power to charge the battery in under 12 hours. Here you can see a general overview of the project. The basic components were a tray for drone landing, a stepper motor for moving the tray, a wireless charging circuit, and a battery management system. The Raspberry Pi controlled the charging circuit and the motor driver. The wireless receiver was mounted on the drone to provide power to the BMS system. This was all powered by a plug-in power supply. Here are a few photos of the implemented tray and enclosure. The clear acrylic enclosure is used to protect the drone from any leaks while also showing off the drone. The BMS system can be seen in the lower right photo. This is mounted in a box to the bottom of the drone. The BMS system can also be seen in this enclosure. Alright, now that we've seen the hardware implementation, I want to pass it on to Gabe for a quick demonstration.
Okay. And that was the tray actuated to turn on the charger. It's just another simple string. Okay, you could maybe hear the relay clicking. To demonstrate, if you can hear the beeping of the smart controller and the LED, that demonstrates the charger's on. And finally, to retract the tray, again, another simple command.
Hi, this is Bryce Hopkins. Now that Dakota and Gabe have discussed and then showcased our hardware design, let's go over some of our software design requirements. So on the drone side, we want the drone to be pretty much fully autonomous. We want to create subroutines that can handle autonomous takeoff, autonomous landing, and any relocalization that's necessary to maintain accurate landings. The idea is that the drone will be flying without any pilot on site eventually, and so we don't want any manual input stages. We want to design all drone side software that way it can accommodate any arbitrary mission that we want to slot in. Our launch sequence and our landing sequence must be pretty self-contained. On the station side, we want all exterior communications to be handled through the docking station. And that docking station will then need to be connected to some sort of Wi-Fi network. That way, all communications to the docking station, such as giving mission information, can be done remotely. We're assuming that the station will have access to a strong Wi-Fi connection and grid electricity at all times. And this is a fairly valid assumption, as our target audience here is a warehouse environment. I'll now pass it back to Gabe, and he can go over our software design.
The main considerations of our software design was to have the system's 2 microcontrollers be able to communicate with one another, the drone's voxel flight and the station's Raspberry Pi. The drone serves as the master on the network. It is hosting the core services of ROS, so that if it were to lose connection, it would still be able to function, and also to minimize latency on the drone side. The station is the slave on the network, meaning it can see the master's processes and receive messages from it. And if the drone were to lose Wi-Fi connection in a larger warehouse, for example, it could still be self-sustaining in its processes, since it is running the master ROS service. Unfortunately, they must be on the same network, Wi-Fi network, for them to communicate, which is something we seek to improve in the future. But the Raspberry Pi should always have Wi-Fi connection for external user control, for which there is a Ubuntu graphical interface.
So in this clip, we'll be showcasing the autonomous takeoff and landing functionalities we've programmed for our drone. We've also set the arbitrary mission of sort of just flying forward, rotating around, and then flying back to the docking station. And we've coded it with the intent that the end user can substitute our mission for any mission that they so choose. So the takeoff and landing are about as modular as we can make them. In this clip, we have a successful landing, but this isn't always the case. We've noticed some issues with our positioning stability of our drone that we'll talk a bit more about later. In this clip, we're showcasing the April tag detection feed present on the Voxlum 500. Note that we did not code any of the April tag detection software ourselves. This is just freely available software online. But it is pretty cool nonetheless, so I want to show it off. You'll notice that the frame rate is actually quite low. We're intentionally doing this because the tag detection software is quite computationally intensive. And you'll see that I didn't actually tape down that tag, so it blows away here. But the tag detection software is quite computationally intensive, so by running at a lower frame rate, we can use more pixels in our detection and detect tags at a higher range. Now I'll quickly go over some project strengths and weaknesses. First up is our wireless charging flexibility. Because it's wireless charging, we don't have to be exactly on the charging pad for it to charge. We can be around 1.5 inches away and still maintain good charging. Wireless charging is also independent of rotation, so we can charge looking at the docking station, looking away from it, rotated 90 degrees, it doesn't really matter. Our April tag relocalization solution is also quite elegant. It allows us to mitigate our IMU and optical sensor drift that we would normally receive over long missions, and really lets us land precisely, or at least know where we are precisely in relation to our docking station. And finally, our greatest product strength is probably our low cost. We built the docking station for under $500, and comparing that to the market options available for docking stations, the cheapest one we could find was around $7,000. So $500 is significantly cheaper than any market option. And now moving on to weaknesses. One weakness is our Wi-Fi dependence of the Pi and the drone. It might be better to change the link to a longer range contact system rather than relying on a warehouse's built-in Wi-Fi system. If there's any dead spots, we'd have to construct code around those and probably just return to home immediately if we lose signal, which isn't the most ideal solution. A second weakness is that the drone's visual positioning requires adequate light to operate. So if the lights go out in the warehouse, our visual positioning is going to be completely thrown off. There's a couple ways to get around this, but honestly, the easiest one is just to make sure that the warehouses have generators that can turn on and provide power backups to the lights to return lighting to the area. Another weakness is an incompatibility with Mavros and Modelii pipe libraries that we found, which resulted in a significantly less elegant April tag relocalization solution. We had originally intended to directly interpret the April tag detections with our code, but unfortunately had to go to automatic relocalization and have those tag detections feed directly into the voxel flight controller instead. In the future, we're looking to get around this in some way, perhaps with a third node thrown in there somewhere that can interpret the tags and then send those off to our main node. And finally, our fourth project weakness is that our drone has a poor ability to maintain its position in the air. We've got a clip for that, which we'll show now. In this clip here, you see us testing out the positional stability of our drone. It's a bit hard to tell from this angle, but we're actually swaying back and forth quite a bit. We'll swap the camera angle here in a second. You can really see it. But our positioning accuracy is really only about a 6-inch radius using visual and IMU alone. And this isn't sufficient for consistent landing. We think the main reason for it is that we're using a 3S LiPo battery, which has a total voltage of 12.4 volts, I think. And the drone was designed to use 4S batteries at 16.8 volts. So despite changing some config files, the motors aren't getting enough voltage to respond quickly enough to any perturbations in the flight. And so the result is that our positioning stability is diminished. The solution should be as simple as buying a 4S battery, installing it, and then changing some config parameters back. Thank you for your time, and please reach out to us if you have any questions.